So let's put all the information we have together and look to see if our inverter satisfies the voltage thresholds for the static discipline chosen by Wintel Corporation. So I've gathered up all my data here. Okay, so here is the inverter that Wintel is considering. Here is a static discipline that it has chosen for all the gates in its chip. When the chip might be a microprocessor that needs to go into a laptop. Here is the picture that I have chosen. So really, the way this would work is that this would be the output, and this part here would have to be interpreted as an appropriate input. So let's take a look at whether the voltage thresholds are satisfied by my inverter characteristics. So from a few minutes ago, the inverter that we built using a MOSFET with a voltage threshold of 1 volt looked like this. So it transitioned at VT equals 1 volt, and then its output was a 0, and it was output was a 5 volts when the input was less than 1 volt. So let's take a look to see if this inverter of ours with the following voltage transfer characteristics shown here satisfies the static discipline. Okay, so let's start. So let's start with looking to see if the inverter satisfies the VOH threshold. So what I'm going to look at is to see if the inverter can reach a high value that is above a 4.5 volt threshold. And so let me go and look here. And if I look here, notice that this inverter does satisfy a high value which is greater than 4.5 volts. So in this case, the high value is 5 volts, and it does seem like it satisfies the high voltage threshold. Let's look at a few more examples because we're going to see this very often, looking at various gates and circuits and look to see if they satisfy voltage thresholds, and I'll try to give you a more methodical way of doing this. So in this case, let's say I have the same inverter and with the same voltage transfer characteristic. And in this situation, let's imagine that I'm looking to satisfy a set of voltage thresholds corresponding to a static discipline that look like this. In this case, my VOL is 0.2 volts. And in this case, my VOH is 5.1 volts. So let's see if this inverter satisfies these voltage thresholds, and I've copied these thresholds out here just for convenience. So one general way that we do these things is we start by taking the input thresholds, and at those points on the input axes, we draw a couple of vertical lines. So for example, what I'll do is for VIL equals 0.5 volts, then we'll draw a vertical line at VIL. That's 0.5 volts. And then for VIH at 4.5, I'm going to draw another vertical line. That's VIH. In this case, that's 4.5 volts. And then what I'll do is for the outputs, I'm going to draw a VOL here and draw a horizontal line in this case, not a vertical line corresponding to VOL. And I'll draw a horizontal line corresponding to VOH. Okay, so in general, when asked to do a problem like this, use this pattern. Okay, draw a couple of vertical lines on the V out versus V in transfer curve corresponding to VIH and VIL, and then draw horizontal lines corresponding to VOH and VOL. And now we can do this very simply. What you will do is you start with, say, VIL, and what you will do is for values lower than VIL, the output should be higher than VOH. And then for values above VIH, the output should be lower than VOL. Okay, so really the valid regions of operation given these curves is here. These are the valid regions. Okay, the hash marks corresponds to valid regions, which says that if VIH is higher than 5 volts, then my output needs to be in that range there. And for VIL less than this value here, my output will be in at that range here. So any transfer curve that operates within those regimes will work. So for example, if I have a transfer curve that looks like something like this, is okay. However, what about the red curve that I have here? Well, since VOH is 5.1 volts and my output of the inverter is only 5 volts, notice that my output is less than 5.1 volts. And so therefore, this threshold is not satisfied by the inverter. So this inverter does not satisfy voltage thresholds. And the reason is that the inverter does not satisfy the VOH threshold because its output is less than VOH. So its high output is 5 volts, and it should really be 5.1 volts. Let's go ahead and try out another example. And in this example, I'm going to stick with the same inverter just for fun. I'm going to pick a new set of voltage thresholds given by this, and I've rewritten those voltage thresholds down here. In this case, I have chosen different values for VIL and VIH, and let us see if this works. So as before, let me go ahead and do the trick I mentioned earlier, which is I'm going to draw a vertical line at VIL and then a vertical line at VIH. So VIH and VIL. And then let me draw a line at a horizontal line at VOL. Let me draw a horizontal line at VOH. And let me see whether this satisfies the various voltage thresholds. So let's start with VIL. For VIL, if I have any value that is less than 1.5 volts, then the inverter should correctly satisfy it. So let's see. For a low voltage, I should have a high output. But notice here, for a value less than VIL, but greater than 1 volt, notice that I don't produce a correct high output. In fact, I produce a low output, and so therefore this one does not work. This one doesn't satisfy the VIL rule. Okay, it does produce a reasonable low voltage, which is nice. It does produce a reasonable high voltage, which is also nice. And for values greater than VIH, the output is less than VOL, so that works too. VIL doesn't work. Okay, so really by the VIL threshold, all the voltages between 0 and 1.5 volts should have resulted in a high output, but in this region, I don't get a high output, and so therefore this inverter doesn't satisfy the voltage thresholds either. Okay, so this one doesn't work according to plan. So remember, in general, you will find that take a voltage transfer curve and draw these pair of horizontal lines for VOL and VOH and vertical lines for VIL and VIH. And then in the example that I've given you, the valid region of operation for a high would have been here and here. So a curve that looked like this, that would be okay. Notice that for the green curve, if my value had been an input voltage less than 1.5 volts, notice that my output is always higher than VOH, I would be okay. However, this didn't work. So any of these cases that I draw here would work. So if I had something that looked like this, this one would work. This would be okay. So this curve is okay. This curve is okay. The main thing to notice is that in the valid region where Vin is less than VIL and Vin is higher than VIH, I need to get the correct outputs. Okay, notice that the static discipline doesn't say anything about the forbidden region between VIL and VIH. Okay, and as a designer, you have a choice as to what to do there. And in fact, for the second curve I've drawn here, notice that it does something funky. It does something funky for VIL versus VIH. In fact, between VIL and VIH in the forbidden region, the output is still high, but it doesn't matter. Okay, the main thing is that the output needs to be valid in for valid input voltages, which is either lower than VIL or higher than VIH.